So then we move to the next speaker. And the next speaker is from Poland. His name is Rafał Walczak. And his title is Transmission Length Tests for Prestressing Cable After Loss of Mechanical Anchorage. And his supervisor is Professor Derkowski. Mr. Walczak, the floor is yours.
Thank you for introduction. My name is Rafał Walczak, and I have pleasure to present a paper of transmission length test for prestressing cable after loss of mechanical anchorage. The supervisor of my work is Professor Derkowski. Okay, to introduce, my PhD thesis is shear capacity of concrete crane beams after an extended period of service in uncertain conditions of prestressing cable anchorage. So one of the part of my work, of my research, is how to determine the transmission length of the prestressing cable in situation of losing of the cable anchorage. So this presentation is actually the presentation of preliminary test of transmission length. So the main goals of this test was to verify the possibility of recording the transmission length for the prestressing cable and to select the most suitable measurements method for further tests. Well, motivation for the research are such pictures we often see in practice. So many of post-tension concrete structures, especially those built in mid-20th century, have no protection on the cable anchorages. And of course, it leads to the corrosion hazard and to mechanical damage exposure as well. So we need, what we need is to create new tools to assess such structures, because many of them are after the design period of use. The specimen on which the test was recorded is the post-tension concrete crane beams, disassembled from the industrial plant. And as we can see, the cable's anchorage have no protection at all, and we can see the sign of corrosion on it. Those are typical I-section crane beams, and they were widely used in Europe in the mid-20th century. That means that many of those structures are still in use widely in Europe, and most of them exceed the design period of use. The subjected beams were prefabricated in 1962, so they are, of course, after 50 years period of use, after designed period. They were pre-stressed with the Freycinet cable, Freycinet type cable, which consists 12 wires, smooth wires, 5 millimeter of each. And here we can see the section with a properly injected cable duct and the wire itself, and of course the anchorage of the cable. The test determined the top anchorage was to cut off to release the prestressing force in the cable with a continuous measurement of the strain changes at the top flange of the surface in the cable region, of course, to record the transmission length of the prestressing force in this cable. We applied 4 independent measuring methods to record this phenomenon. First, electrofusion strain gauge system, digital image correlation method also, and distributed optic fiber sensing with a static approach and with an independent high-frequency approach as well. The test setup scene, we can see that DIC photos were taken from a steel frame above the top surface of the element, from the above. And on the top surface, the optical fibers were installed in such pattern, as we can see in this figure. First, 3 traces, colored blue, labeled DS, was to record longitudinal strains and deformation. Each trace has 2 lines, as we can see in the picture. Also, the perpendicular was installed, the red one, the P section, in order to record transverse strain at the spacing of 300 millimeters, as we can see in the figure. And last but not least, the D section, which was placed at the axis, above the axis of the cable, in order to perform high-frequency measurements. As fibers, the standard telecom optical fibers SM9 were used, which were glued to the surface with epoxy resin. Of course, optical fibers were connected to the optical backstacker reflectometer and optical interrogator for the high-frequency measurements. Also, conventional spot strain gauges were installed. As we can see in the picture, they were installed at the bottom surface of the flange. It was in order not to interrupt the photos, the DIC photos, which were taken from the above, because the cables will interrupt the photos. So the strain gauges were installed at the bottom. And as a result, the sensors were at the greater distance from the cable axis. So the recorded strains were lower, but our main purpose was to record the transmission length, so the strain value were not a priority. The cutting of Anchorage was performed by a circular saw in order to release prestressing force gradually. And after the cutting of Anchorage, we could observe incomplete filling of the cable duct, which was often seen in practice. And this result was that 4 top wires were actually work as unbonded. So we could record this later. After the test, the cable duct was opened, and we can observe that 4 wires were at the first, but 2 wires were unbonded through the whole length of the element. Yeah. Later, we cut out a section of the profile, and we could observe that bottom cables also has the same problem with incomplete filling of the cable ducts. Okay, and moving to the results of the experiment, here we can see on this graph longitudinal strain changes from the all of the optical fiber ducts, and we can see that longitudinal strain are decreasing asymptotically, but not to the zero value, of course, owing to the unbounded wires, which we could see in the duct. Okay. Then this graph presents a record of the transverse strain observed, and also we can see the asymptotically disappearance of the strain, actually almost to the zero value. Distribution of the optic fiber over the surface could enable the visualization of the phenomena. And on the left, we can see a graph which represents longitudinal strain changes. So we can see, of course, tension strain due to loss of prestressing force in the cable. And on the right, we can see transverse strain changes. And of course, in the region of the cable, we can see a compression perpendicular to its axis. High-frequency DOFS recorded gradually transmitted prestressing force, which led to the change of the strain, as we've seen in this graph. We observed the six grades of strain changes, and here I can present the video of the test and continuous measurements of the strain through the length of the element with a high frequency DOFS. Actually, the frequency was 80 Hertz, so it was very high, and it was very high amount of data. And at the first, we can see that the top one wires which were unbounded were cutted, and the constant change of the strain is visible on the length of the element. But some bounded wires are actually cut out too, and they represent the transmission length we can observe at the first of the beam part. And right now the anchorage will be cut off, and it's the final graph. Okay, here is a comparison of the strain gauge in one point, in one gauge, and the high frequency DOFS in one point in time domain, because those measurements were continuous in time. And of course, as I said, the strain values from the gauges are lower because of the localization of the sensor, but they are consistent in time. The same gradually graded of strain are observed. Unfortunately, DIC method does not record the change of strain, mostly due to splashing water during a cutting, which changed the shape and texture of measuring markers. So the strain map was just a blur, unfortunately. And here we can see the summary of the test results. This is a graph with all the measurement methods presented along the element. So we can see the red one, high frequency DOFS, and static DOFS with a blue color, which represent almost the same phenomena. With a violet color, we can see strain gauges. Of course, lower value due to the localization of it. And the green colors represent transverse strain recorded with a DOFS. And the transmission length were arbitrarily considered to be at 1.1, 1.2 meter from the start of the beam. And the conclusions from this test: in case of failure of prestressing cable anchorage, asymptotic disappearance of strain changes over the transmission length can be observed. Then the prestressing wires, which were not wrapped, which were unbounded in cement ground, have lost their prestressing force along the whole length of the element. Also, the DIC method is not actually suitable for testing in presence of water, so we neglected this measurement method in further research. And the optic fibers measurement enable precise determination of the transmission length of the prestressing force and extensive analysis of the phenomena, of the transmission length phenomena. Thank you very much for attention, and I'm open to your questions.
Thank you very much for this very interesting presentation. I'm sure that many people in many countries will follow these results because they all have the same problem, that they are about at the end of the service life, which was planned, and there are many questions what to do with these old structures. And the problem is that we do not know too much about it, and this is really contributing to our understanding.
Yes.
Let's have a look to questions. Oh yeah, there is one question, and this is, what is your explanation for the local peaks of strains that you have obtained?
Well, thank you for this question. I will just jump to the slide. Yeah, so the local peaks we can see here, and we are not, we don't have 100% to know this, but we think that it's those are cracks which occurs at the very early stage of concrete head rotation, so almost 50 years from now. And they width are just increasing due to release of the prestressing force, due to loss of the prestressing force. Actually, we have a new microscope in the lab, so I will try to explore this crack. Is this correct? We also think that it could be the cracks because the stirrups were at this spacing, so it's highly probable in our opinion.
Okay. Another question from Hussein Nasser. Did you apply a speckle pattern to monitor with DIC?
Yes, of course. We applied the speckle pattern at the top. So first of all, we had to install the optical fiber sensor, and then we painted it with the bright color and with a black speckles pattern, of course, to record the DIC strains. But unfortunately, the record of this method wasn't accurate.
Okay. Okay. I have another question. You have now measured the strains, and in this way you can conclude on the transmission length.
Yes.
And it looks not too bad, I would say, because you said it's about 1.1 meter to come back to nearly zero, but yeah, also for 0.4 meters you get already quite a bond force is transmitted in the concrete. So, but another thing is we know now that, but we need also the anchorage length, and we measure the deformations. But can you say also something on the anchorage length in combination with that?
Well, it's a very hard to determine it. What we are coming up to determine the strain, because it leads us to what is the response of the structure when we lost the prestressing force. So for a practice, for a situation in the practice with those structures, this is most important. And later on in the research, it is planned how the transmission length, the losing of the anchorage, resulted in the capacity at the shear, because the crane beams, of course, can be loaded nearby the support, so the vertical forces are very high, and we will observe first of all how the transmission length goes with these tests, and then on how the capacity is lower, and it is lower, of course.
Yes, you know now more information because you have opened the ducts, and you have shown that even two wires were totally unbonded. So if you know that, then I think you can also conclude on the anchorage length, but then only, of course, for this particular case.
Yeah.
The question is, with this knowledge, what can you say about, can you use it for other bridges, typical, this type of bridges, for instance? Because this is very important to see this for a single bridge. And but can we use that knowledge for more bridges, or do we have to do a lot of more research?
Fortunately, those type of prestressing cables were widely used in Poland and I think in many other European countries. So the precast post-tension concrete, which were made in mid 20th century, were in most cases in this technology. So we can move this research to wide amount of the other typical members of the construction members. But of course, it depends very much on, for example, of the filling of the cable duct, because as we see in the practice, the technology was developing through the years, and it is highly recommended to see what's in the cable duct, of course. Right now, when we because this was a preliminary test, but I conducted another those type of tests, and I could observe very good cable duct fillings with all bonded tendons, and actually very poor filled cable ducts. So we have almost two variety of samples.
Okay, that's very interesting. If we widen the picture a little bit, then of course the question is, how can we make a risk analysis of bridges? What would it mean, for instance, when the when the anchorage breaks and we have to rely on the slip? And you said you also look to the shear capacity. What would it mean if this happens? Is the bridge then really near to collapse, or can it really collapse, or is there still a margin to this? Can you say something in general about this?
Yeah, I think that it will not collapse, of course, suddenly. Maybe due to fatigue, because it may be the case. It is. I think it's interesting topic for further research. But just losing of the cable anchorage, I think, would not cause collapse in most cases. But my idea to represent this research in practice was to, if we could safely ensure of safely operation of such structures, because there are many of such structures in European countries, and the owners of such facilities are concerned about the technical conditions. So if we could show in the research that the failure of the anchorage would not lead to sudden failure of whole members or whole structure, that means that they can be used. And of course, if we've seen that cable anchorages are failed in the member in the hole, we need to test it out, of course, but we can use it over a period of use because it will not fail suddenly.
Well, that's indeed good news, but we have to satisfy the demands, of course. And
yeah.
Well, another question by Jean-Luc Clément: are you planning to perform a numerical simulation of your test?
Yes, of course. I plan to do this because we operate on the members dismantled from the hull, so we have a limited number of specimens, and it is very good way to verify the numerical model with those research and perform numerical simulation. But I will do it in the future, so I cannot present it right now. But of course I will.
Okay, that's good. If you have such a case and you have a bridge or beams as a part of the bridge which are not satisfying the structural safety demands, then you have a number of options. whether you have to tell that the bridge will be closed because it's too dangerous or demolished, or you can strengthen it if possible, or you can say, well, it shows that it is not too bad at this moment, so we can, with better inspection, we can extend the service life with some years. What is your opinion about strengthening of this type of bridges? Do you have any ideas about this?
Yes, I will try to examine this problem, but I think it's very hard to strengthen it because we cannot we cannot pre-stress those cable which lost their anchorage. Of course, we can strengthen the shear region, and it may be case because many of those structures have very low transverse reinforcement ratio, and the shear capacity can be crucial in those structures. So, but it's very hard to get greater value of the shear capacity. Actually, many of the specimens at the shear lead failure due to compression strut crash. So it's very hard to strengthen it. But of course, it is possible, and it will be researched further on.
Okay. Are there any questions more?
Maybe I ask one question.
Yes,
hello, Rafał. I don't understand. Maybe I missed something. Why do you choose to cut off upper anchorage in the stress zone? Not lower anchorage, only upper anchorage.
Yeah, it's a very good question. I didn't mention it. We decided to cut off the top one because it's the easiest example. Actually, we can measure the transmission length the easier on it. But later on, another research, I will cut off the two lower cables, which are of course in tensile zone. Which determine the capacity the most. So we decided to cut off the top one in order to record the transmission length easier, because it's the less complex situation, because at the bottom we have two cables in the two sides. And the top one is only one, so it's less complex issue, and we could analyze it in the best way.
Okay, so and one more thing, what was the supports of a beam? Is it necessary to take design supports in 2 points, or you put it only on the ground, or only supports by length of the beam?
Well, I support it in the 2 points. It worked in the whole as a simply support beam, but in the transmission length test, it's not the case, because
it's not the case,
because we just record what's after what's the consequence of the loss of prestressing force. So the support does not really matter. But of course, it matters in a capacity test later on without the anchorage of this specimen.
Okay, thank you.
Okay, thank you. I think we are at the end of this presentation, and I would like to thank you and compliment you with the very clear presented work. And I think that's really very important for all of the European countries to know these results, not only in Poland. So please, if you're ready, write some paper on it, an international paper, so that we can also use it in other countries.
Of course I will. Thank you very much.
Okay. I think we are at the end of this session now, and I think that it was very interesting 4 totally different topics and all very well presented and all very relevant and with a scientific background. And it shows really that the research which is being done is contributing to the needs of society, I would say. And I would like all the speakers for their very good work and wish them success with finalizing it and presenting it and publishing it. And I like also to ask to thank all the people who are there, supported it, and came up with questions to make it more valuable. So thank you very much. And I hope that you will have a good closure of this very interesting conference. Thank you.